Hi class. Alright, so today's chapter is chapter 9 on tides, and this will look at how the sun and the moon affect the tides here on Earth. So first off, what are tides? Tides are just the periodic rising and lowering of the sea level. So the height of the water level will change throughout the day. And this is caused by gravitational attraction and the motion of the sun and the moon on the earth. So if you look at the image below on slide 2, you will see that the sun and the earth are a certain distance away, but because of the size of the sun, what's known as the barycenter is closer to the sun. And that's because the two objects are not rotating around one another, or no, the earth is not rotating around the sun, more so both the sun and the earth are rotating around each other. So when you do that, you have a center, a barycenter, that is offset towards the largest object, which is the sun. And this can be explained using Newton's law of gravitation. So next, let's talk about this gravitational force, because that's essentially what's causing these two objects to rotate around each other. So gravitational force was derived from Newton's law, and it essentially says that every object that has a mass is attracted to every other object. So henceforth, the Earth is imparting a certain amount of gravitational force on the sun, and likewise the sun is exerting a gravitational force on the Earth. Now this Newton's law also states that as mass increases, so does the gravitational force. So because the sun compared to the Earth is much larger and has a greater mass, therefore the sun's gravitational force is much greater. And then when you add distance into it, as distance increases, the gravitational force greatly decreases. So even though the sun has a greater gravitational force because of its mass, if you look at the distances between the sun and the earth and the moon and the earth, the moon is much closer to the earth, so it has a much more greater gravitational force on the earth than the sun does. So you can see the image on the left hand side where you have different size masses, and it depends on how far away that large mass is to an object. That's how much gravitational force it will have. So when you look at the equation on the right hand side, you can see that the distance, which is r squared, is on the bottom. So when that's on the bottom, that means if you are really far away, you're going to have less of an impact than if you are closer to the object. Now, that's just one type of force that affects tides on Earth. The other one is centripetal force, and this is similar to Coriolis that we were talking about when we were talking about waves, and this essentially just deals with the spinning of the Earth. And so you have a center of mass, so let's just say the core of the Earth is the center of mass, and you have an orbiting object around it. And so when you have the moon orbiting around the Earth, that moon is imparting a centripetal force on top of the Earth. So as it's moving, it'll continue to rotate around the Earth until it no longer has that force being put on it. So for instance, in the image below, that boy is holding onto a string, and at the end of the string there's a ball, and he is rotating around himself. But the moment that string snaps, that ball will no longer rotate around the buoy, it will follow the green arrow and it will continue in the direction at which the momentum of inertia is going towards. So that centripetal force is really what holds the moon towards the Earth, in addition to the gravitational force. So let's talk about that now. Let's talk about both of the forces combined. So when you combine the forces, that's when you get resulting forces. And you have two different ones. You have zenith and you have nadir. Zenith is the closest point to the moon on Earth. So in the image below, you can see that point A is closest to the moon. So that would be the zenith. The nadir is the point that's furthest away from the moon. So you can see that the nadir is point C because it is the complete opposite end of A in correlation to where the moon is at. And then all the other forces point towards the moon, but they are not at the zenith and they are not at the nadir. Tide generating forces. So when you combine all of those gravitational force and the centripetal force, you get you can either get small changes in tide, you can get no changes in tide, or you can get really large changes in tide. And it just depends on where you are on Earth. So if we look at the image, let's look at point Z, because that's your zenith, compared to where the moon is at in relation to the Earth. And you can see the black arrow is for your gravitational force. So at that point, your gravitational force is going to be the largest compared to everywhere else on Earth. Then, if you look at the red line, the red arrow, that is your centripetal force. That is equal around the Earth no matter what. So it is pointing towards the Earth. It imparts, there's no difference no matter where you are on Earth. It's always going to be the same amount of centripetal force on the particles. And then when you combine those two, so you have to subtract your gravitational force minus your centripetal force, and then you get your resultant force. And that will tell you what direction and how powerful your tide generating forces are. So if we look at the zenith, that point Z again, you can see that the blue resultant arrow is pointing towards the Earth, towards the moon, right? So that means that at that point on Earth, the tide will be pulled towards the moon. Now let's look at the opposite end, at the nadir. You can see there's a very weak gravitational force, so a very short black arrow. You can see the centripetal force is equal. There's no change in that. So that red arrow should be the same size as the one at the zenith. And when you subtract those two, you actually get a negative number. So that means the resultant force, that blue arrow, is pointing in the opposite direction, right? So this is how you get two bulges of tides throughout the day. Right? And you can look at the other different points and you can see the gravitational force pointing towards the moon. You can see centripetal force is the same no matter where you are. And then when you look at the resulting force, you can see at different parts it points in different directions. So at the South Pole, you can see that the resulting force is pointing north towards the equator. And likewise, if you look at the North Pole, the resulting force is pointing down towards the equator. So here's just a summary of what we talked about. So the top is just your gravitational force, right? And all the arrows are pointing towards the moon. And then if we look at the resulting force, which is the bottom, you can see that you get the arrows at the zenith and the nadir pointing in opposite directions. And so it causes the water to bulge on either end. You also have a squishing of the tides at the north and south pole, so that further amplifies the bulging on either side of the Earth. So you have a tidal period, just like wave periods. They all have different timing. And so you have what's known as a lunar day and a solar day. Now, depending on which one you're looking at, this will vary. So on a solar day, this is what we use every day. It's just the time it takes for the sun to revolve around the Earth one time, right? Until the sun is overhead on the next time. So that's generally 24 hours, right? And that doesn't change. Now, if you are looking at lunar day, now this one's really interesting, because your lunar day, if we start with the moon smack dab above at hour 0, if we look at the image below, and you can see that as the man on the Earth is rotating around, by the time he gets all the way back to where the moon would have been at 24 hours later, the moon's not there. It takes the man another 50 minutes to get to where the moon is directly overhead again. So this extends the lunar day by 50 minutes. So your lunar day is 24 hours and 50 minutes compared to your solar day, which is just 24 hours, right? That's because the moon is rotating around the Earth, whereas the Earth is, technically speaking, rotating around the sun. Okay? So looking at this, you can see that the sun has a far smaller effect on the tidal bulges on Earth than the moon. The moon has a greater influence, primarily because of how close it is to Earth compared to the sun. The sun is much further away, so even though it has a larger mass and it should have a larger influence, the distance, because it was r squared, the r squared was on the bottom of the division, that greatly decreases the sun's influence on the tides. But the sun still has an influence, a really small influence, which you'll see later on in the presentation. But the greatest influence is from the moon on our tides here on Earth. All right, so now let's look at the different types of tides that we have here on Earth. And let's start with the spring tide. Spring tide is when you have the moon in line with the sun and the Earth. So if you have a new moon, that means the moon is in between the sun and the Earth. And if you have a full moon, then the moon is on the other side of the sun, or other side of the Earth. And so you have sun, Earth, moon. Okay. So when you have a new moon, that bulge that's next to the moon would be known as the lunar tide. And then on the other side, it would be known as a solar tide. All right. Now, if we look at the second type, we have neap tide. Neap tide is where the moon is perpendicular to the sun. So you have sun, Earth, and if you're on the north, if the moon is up by the North Pole, then you have a third quarter moon, and the lunar tide would be right there facing the moon. And then if the moon is by the South Pole, you would have the first quarter moon. And then your solar tide would be the tide that's being pulled by the sun. Okay. So now if we look at the two different types of tides, spring tide and a neap tide, the spring tide should be the largest because it is you're adding both the solar and the lunar tide together, whereas in a neap tide, your tidal influences are going to be smaller, shorter, because the lunar tide is opposite from the solar tide. Now let's look at the phases of the moon, okay, because this will determine what type of tide you have. So you can see if the moon is in between the sun and the earth, you have your new moon, and your full moon is just the opposite side. You've got your third quarter and your first quarter, so those are your neap tides. And then in between, you have different phases. So in between new moon and third quarter, you have your waning crescent. So that just moves the lunar tide at a 45-degree angle. Then between the third quarter and the full moon, you have your waning gibbous. And then between your new moon and your first quarter, you have your waxing crescent. And then between your full moon and your first quarter, you have your waxing gibbous. All right, so it's just depending on which phase you're going into, you're either waning or waxing. Okay, so the Earth's orbit, this is the Earth's orbit around the sun, and this has an effect on the solar tide. So when the Earth is at the perihelion, that is the closest point to which the Earth is near the sun. And then the opposite would be the aphelion, which is when the Earth is furthest away from the sun. Yeah. And then if we look at the purple circle represents the moon's orbit around Earth. And same thing, it has its closest and furthest point. So the closest point to Earth would be the perigee, and then the furthest away point would be the apogee. So that's that. So depending on where the Earth is compared to the sun and where the moon is compared to the Earth will determine whether we have really large tides or if we have really small tides here on Earth. So this next slide, you can just see a little bit more information. You can see actual distances between the Earth and the moon. And so you can see at the perigee, the moon is about 362,600 kilometers away. And at the apogee, it's a little bit further at 405,000 kilometers away. So when you are looking up at the night sky and you see the moon, you can kind of get a sense of whether it's approaching the perigee or if it's approaching the apogee. Because when we see the moon on Earth, if it's at the perigee, it's going to be a lot larger. It's going to look a lot larger. The moon is going to look large versus at the apogee where the moon will look kind of small. So Earth's rotational effect has an influence on the tides. So let's look at this image here. The man is standing at the 28-degree latitude line, and you can see that the moon is directly overhead. And you can see that he is in the high tide. So if you look at the graph on the bottom, point A is where the man is standing at, and you can see that the tide is higher there. When the man rotates away from that tidal area, you can see that the tide decreases. And then he continues to rotate, and you can see at point C, he is now at the edge of a tidal bulge. So you can see the tide goes up just a little bit, but not that much. And then he continues to rotate. So at point D, he's back to a low tide. And then at point E, he returns back to the high tide point. And that's all within a 24-hour period. But you can see it depends on where on Earth he is at, because if you look at the 0-degree latitude, let's just say we put the man at the equator, he won't experience as high of a tide because he's never really directly in the middle of the tidal bulge. You can see he does have high tides, but they are equal or about the same height throughout the day, versus at 28 degrees north, he had a much higher tide and then he had a lower high tide. And that's the same if we put him at 28 degrees south latitude. Tides in the ocean look like free propagating waves with crests, but they are separated by half an Earth's circumference, or about 20 kilometers or 20,000 kilometers. So in an ideal Earth that had no continents, you should expect tides to just freely propagate around the Earth's the ocean surface. But because we have continents, it creates what's known as amphidromic points. And these are areas where there is no tidal influence whatsoever. And then off of these amphidromic points, you can get cotidal lines. That is where you have high tides occurring at the same time. So there's an image in your textbook that you can look at for these particular definitions. Oh, never mind. I have a slide right here. You can see the amphidromic point is labeled as AP. It's the red dot in this figure. And you can see that depending on where the high tide is and where the low tide is, the orange arrow is your cotidal line. So it will rotate around this amphidromic point, and as the tide is rotating around. So you can see at the point itself, there is no change in tidal height, but everything around it is changing. Okay, and this is purely created because of continents. If there were no continents, we would have no amphidromic points. Okay, so the continents also affect the tides, and because the tides influence the biological structure on the coastal regions. So you can see in this image below, you have a distinctive upland where no tidal influence affects that line. But if you were to have a really large storm, you can see that storm log line is where it will get up to at the highest point. Then you have your supratidal, your intertidal, and your subtidal. So your subtidal is the area which is always completely submerged, and it's never to the point where it dries out. And that's your mean lower low water level. So when there is it's when you have your lowest tide, that's where the line would be at. Your intertidal region is the area in which it can be submerged part of the time, but depending on what the high tide is doing, it will either be submerged or exposed. And so that mean higher high water is basically the point at which you have your highest high tide. And then at that highest high tide, that's when that entire region will be covered. Supertidal is only when you have really extreme tidal events, and it should not be covered. It should be exposed most of the time. So we have 3 different types of tides. We have a diurnal, which has only 1 high tide and 1 low tide per day. So within a 24-hour period, you only see 1 high tide and 1 low tide. Your semi-diurnal has 2 high tides and 2 low tides that are the same height. So in a 24-hour period, you'll see 2 high tides, you'll see 2 low tides, but they will be the same height. And then you have your mixed semi-diurnal, and that is 2 high tides and 2 low tides that have different heights. So you'll have 1 higher high tide and 1 low high tide. So here in Hawaii, we experience mixed semi-diurnal tides because 1 high tide will be higher than the other in a 24-hour period. So here's just an image of what those different tides look like. And depending on where you are around the world, you'll experience different types of tides. So you can either get a diurnal tide, which is the top one. So you can see between the two red lines, there is only one high tide and one low tide. Versus semi-diurnal, where you can see the tides are more or less the same height, but there are two high tides within the day and two low tides. And then if you have mixed, you can see that there is a distinct difference between the two high tides. So one is higher than the other, but you still have two high tides and two low tides. So you're going to have one higher high tide and you're going to have one lower low tide. So it's going to get pretty, that intertidal region is going to get really exposed during that lower low tide. So something to keep in mind with tides, there is reflection and amplification of tides, and this is primarily due to the interactions between the sun and the moon on the earth. So if they're both in line, then you can expect an amplification of the tides. You can also have a reflection of the tides, like off of different objects and whatnot. You can get standing waves, you can get tidal bores and whirlpools off of tides. You can get tidal currents. Lakes and ponds on land can experience tidal changes if they're deep enough. And a lot of biology use tides and phases of the moon to indicate when they should be spawning or reproducing. So that is chapter 9. So hopefully let me know if you guys have any questions, and make sure you guys read your textbook. Okay.